Hey everybody. So I had a little bit of an issue recording a lecture yesterday, and hopefully it doesn't crop up today. So if you're watching this video, then I have figured out a way to record it and gotten over my blue screen of death issue. If you're not watching this video, then all I'm saying right now doesn't matter. So last time I did have kind of a long video, but it's a very detailed and important topic about how Hamiltonian Monte Carlo, which is the third MCMC algorithm we talked about, generates its proposal. So I have a very brief summary right here in front of me. So we start at some random location. We impose a random flick of our little marble or particle in some direction out of a 2D multivariate normal. In this case, it's 2D. If you have more parameters, it's however many dimensions you have parameters. And the particle then starts to interact with the gradient of the posterior that you see in blue there. And so it follows, the particle follows the posterior for, in this case, however many leapfrog steps we specified, it's 20, where each step size is specified to be 0.01. And therefore, it ends up right here, the proposal. This proposal is then accepted or rejected the same way as we did for Metropolis-Hastings. You go the height of the posterior at your proposed over current, compare it to a number between 0 and 1. The only thing that's different is we incorporate the momentum as part of this decision. Just wanted to write that down. And of course, I'm struggling. You know what? I don't think I will finish writing this. The momentum variable is a part of our accept versus reject decision. Okay. Last time I finished by going through our good old example of mouse data, where I use the Weibull distribution and really show you how that trajectory is generated. Today, I want to kind of finish the lecture and then go into R and show you sort of the application of all three MCMC algorithms. And then we're going to compare their efficiency. So first things first, this only applies to HMC. Our posterior is perfectly smooth. In fact, HMC doesn't work for categorical posteriors. The posterior function has to be smooth so that the particle can skate along and the trajectory idea can work. But for us to implement it using a computer, we're going to approximate, right? We're going to use discrete segments. And we notice that, as you might intuit, the smaller the step size, the better the approximation. So this particular particle on the left follows the contour much more closely than the particle on the right. So when our step size is too big for the posterior, when our step size is too big for the posterior, it's not the right combination of the length of the trajectory and how, the curvature in the posterior, we see that we can have a divergent transition. And here it occurs with this combination. just, we're trying to sample from this very, very correlated set of parameters. The black trajectory uses teeny tiny step sizes, and it doesn't move that far. So it's very good. The approximation is very good. The blue trajectory uses fewer steps, but each step is big. And the blue trajectory is inefficient because it turns back on itself. We pushed the marble too hard to where it rolled to the other side of the room and it came back. The red trajectory increases the step size only a little bit, but it just basically skates off the posterior. So the red line is what is called a divergent transition when our approximation fails to work. Our approximation of what the true trajectory would look like fails to work, often because our step size is too big. And divergent transitions end up in a sample not being taken. No sample, no proposal made, and no sample taken. So this is problematic if you have an area of the posterior where your particles can't go. If there's a systematic bias to where there's an area of the posterior where your particles can't skate, then we're basically going to overstep that area. So in this case, these tend to occur in, particularly curved areas of the posterior. Tend to happen in areas of high curvature. So we're coming along and we're exploring our posterior. We get to this spot, which is an area of curvature, and our marble doesn't skate into there. And so we end up getting no idea. We can't resolve that area of high curvature. So our chains are biased. Any divergent transitions should give us pause, because that means we could not correctly explore all the areas of the posterior. It might be the case that it's actually the most interesting area of the posterior that we're missing, but it doesn't matter if you're interested or not. Like you might not know in high dimensional space what exact area of the posterior you couldn't get into. If you see any divergent transitions, your trajectories weren't precise enough to explore these areas of high curvature. So now, of course, if you run 10,000 samples and you have one divergent transition, this just happened due to numerical rounding, or this is just a random numerical error, not often a problem. But once you start to go to something like 10% divergent transitions, even 5% divergent transitions, or if all of your divergent transitions are concentrated in a single area of the posterior, we have no idea. Yeah, we get a biased view. We get a biased posterior. The true posterior looks like a funnel, but our samples stop like right there. And we can't see how far down that funnel goes. If we can't see how far down the funnel goes, our intervals for theta 2 are going to be biased. Funnels are known to be, and by the way, this too, you see, is a funnel. Funnels are known to be particularly problematic areas for really, I think, all samplers, maybe except for Gibbs, because Gibbs knows exactly the distributions, or pretends to, because we're using the recipes. So if you're plotting your posterior and you see the start of a funnel, that's reason to reparameterize your model, because there are known issues around how well these trajectories work around funnels. But typically, what the authors of the STAN package suggest is if you get a lot of divergent transitions, a good first step might be to reduce step size, to make the step sizes small so you can actually walk in these areas of high curvature. But there will be spaces where no matter how small your step size, you still will not be able to walk in. Just to be clear, if there's a problem, the package will output that there was a problem. Okay, we've seen a few scenarios where our samplers have generated U-turns. For example, right here is a U-turn. For example, right here is a U-turn. Right there is a U-turn. Right there is a U-turn. Right there is a U-turn. Specifically, the picture on the left features relatively few such U-turns. Maybe over here, maybe over there. We really want to avoid U-turns in a Hamiltonian Monte Carlo analysis. And so the package that our author uses in his kind of standalone software, the package that I will show you called BRMS, which is just a wrapper function to STAN, it has programmatic code that detects when a U-turn is coming and cuts off the trajectory before the U-turn occurs. It has a complicated set of criteria that I frankly do not want to get into. They're listed somewhere. I'm sure we can all read them. It's trying to detect if the ends of the trajectory are still getting farther apart or they have started to get closer together. And once it detects that they started getting closer together, it cuts off the length of the trajectory. So during the warm-up phase, STAN tries to optimize the length of each trajectory. And once the warm-up stops, it uses the same step size and trajectory length to explore the rest of the posterior. So during the warm-up, it's exploring, kind of sending out exploration type trajectories to figure out what is the optimal step size and optimal trajectory length for your exact posterior. Once it finds that, post warm-up, it goes and does the sampling the same way as I've showed using kind of a classic Hamiltonian Monte Carlo. So I'm doing arm wavy things because, quite frankly, I do not want to get into the code about how STAN detects when a U-turn is about to occur. It's complicated, and it's even hard to find what the exact code is. I'd rather show you some practical use of our three major MCMC algorithms. By the way, there's many more than 3 MCMC algorithms. Many, many, many more than 3. For example, think about the way that you can combine something called the Metropolis within Gibbs. And I think I'm getting a little ahead of myself. There it is. Gibbs, being as efficient as it is, where you use some mathematics to figure out the posterior distribution of certain parameters, you can combine the Metropolis-Hastings with its random walk and the Gibbs with its really good known recipes for something called Metropolis within Gibbs. Together, they're probably increase your efficiency even further. For parameters that have conjugate priors, you use Gibbs. For parameters that don't have conjugate priors, you use Metropolis-Hastings. I have seen some ideas about HMC within Gibbs. Now, HMC requires that we compute gradients. So each HMC sample takes a little bit longer, but it tends to be far more independent. The successive samples end up at very different ends of the posterior distribution. And this is because of that no U-turn property. And so, HMC within Gibbs Makes a lot of sense. I'm not aware of a package that does it. That it might exist out there. I'm just not aware of it. And so this would need to be coded by hand. But if for a problem that is difficult enough, I'm sure there are people who would. There are plenty of cases, for example, multimodality, and I have multimodality here, where all MCMC samplers are going to struggle. Because whether it's, by the way, this little test, what kind of MCMC am I running right here? It's HMC, right? Because we have a curved trajectory that's following the bowl created by that particular normal distribution. So there's actually 3 2D normals. And if we let an MCMC loose, it might get stuck on any one given node. And it might take a while for it to jump over to a different mode. And you can see we're not even seeing this other mode here. It depends on a lot of things. It depends on how long our trajectories are allowed to be. It can depend on how big the proposal standard deviations of a Metropolis-Hastings are. So multimodal posteriors might be where all MCMC algorithms are going to struggle to resolve all the modes. It depends on a lot of different factors, and they take a lot of tuning. Finally, you might intuit that MCMC can get quite complex. Every algorithm, and there's many, requires its own set of tuning parameters. Metropolis-Hastings requires tuning of the proposals. Gibbs requires us to know conjugate priors. Stan requires we understand these trajectories, and so requires that we, tune the step size and the trajectory length. But I don't want you guys to lose sight of good science. Good MCMC does not cure bad science. Good MCMC does not cure a badly specified model. If you should be using, if you're analyzing counts and you're for some reason using a normal distribution, no amount of good MCMC will fix the fact that you shouldn't be using a normal distribution for counts. Not anymore, not when there's so much software available. However, if we don't pay enough attention to MCMC, we can definitely fail to answer good scientific questions. And if we fail to pay attention to MCMC and, for example, produce chains that are too autocorrelated, we can really bias the uncertainty inside the parameters. So in this super computational world of data science, we have to pay attention to both. We have to pay attention to all 3. Good MCMC, good statistics, good science. And science comes first. I think science comes first, statistics comes second, because frequentist analyses still work just fine in many cases, and then good MCMC. Let's not forget the key concepts that we learned. Remember, we haven't talked about setting priors in a little bit, but we learned about how to run prior predictive simulations to pick weakly informative priors. We learned about how to assess convergence. Our hat's near 1, and we'll look for chubby caterpillars. And I can't spell that word for the life of me. So that's a chubby caterpillar. I think if you actually Google chubby caterpillar, you get that picture when I was putting these notes together. So when we plot our trace plots, we're looking for chubby caterpillars, not slithering snakes. We're looking for effective sample size that is as close to the number of samples you requested as possible. We're looking for no divergent transitions. Divergent meaning that our simulated trajectory has diverged from what the true trajectory would look like if we used infinitely small step sizes, and good science above all else. All right, off my soapbox and into R. So I thought that I would show you what I like to call a linear model 3 ways. It's kind of like you come to a fancy restaurant and they say, we're going to give you pinto beans 5 ways, and then there's $50. We're going to do a simple model 3 different ways. This is a model from our last activity where we have chloroform A in our North American freshwater lakes, and we're analyzing the impact of temperature at the lake on this chloroform. Last time we saw that, and this is just an OLS model for reference, not surprisingly, there was a positive slope between temperature and chlorophyll A, because chlorophyll tends to reflect the amount of productivity, sort of bioproductivity inside of the lake. Okay, so I will start with the description of our model. Right? We had practice doing this in the homework, practice doing this in the activity. My outcome variable is IID normal, where my mean varies with temperature, and my residual variance, my standard deviation, is stationary, does not vary with temperature. I will use a normal 3-2 prior, a nice weakly informative prior. I even included a little bit more prior uncertainty than what we saw in the activity. And the reason why this is at 3, if you recall, I'm using a centered temperature, and then alpha just picks off the mean of the outcome variable. The mean is very, very close to 3. So this is a very, very reasonable weakly informative prior for our intercept alpha. When we use a centered covariate, we can center the prior at 0. And so this is a very reasonable weakly informative prior, where a priori, we're not assuming any particular direction. This always makes me comfortable. I let the data push the prior in one direction or the other. And finally, for our sigma, lots of choices. For simplicity's sake, I'm running with the exponential 1. Other choices could be a gamma, a log normal, a half normal, excuse me, a half T, half Cauchy. But for now, we're focusing on understanding the differences between the 3 kinds of MCMCs. So I'm running with just a simple exponential 1. All right, first things first, we'll be using the MH adaptive package. I'm doing my best to focus on real packages that could be used for real analysis. And MH adaptive is the adaptive variant of the Metropolis-Hastings. It's the one where it computes the correlation among the samples taken thus far and can actually deform that proposal distribution to hopefully better fit the posterior. So, you probably have to install it anew. So go ahead and uncomment that line 23 for that. The first thing I need is an R function that produces our unstandardized log posterior, what our log posterior is proportional to. So it's a function of our parameters, our outcome variable, and our covariate. And just to make reading code easier, I will take the first parameter to be the intercept, the second one to be the slope, the third to be the residual standard deviation. This should all be really familiar to you guys. Here is my log likelihood. I can sum because I'm taking logs here, and I can sum because of IID. Here is my data inside of Y. Here is my mean that varies with X. Here is my standard deviation that is stationary, does not vary at all. Here is the sum of my priors. Recall that we assume our priors are a priori independent. I set the 3-2 normal prior for alpha. I set the 0-2 prior for beta, and I set the exponential prior for sigma. I add them all together because I have log equals true inside of each prior. And now finally, of course, what the log posterior is proportional to is the sum of my log likelihood plus the log priors. So here is my function, and it needs to be our function. And now I can plug it into this Metro-Hastings function that is a part of the MH adaptive package. So here is my function that produces the unstandardized log posterior. Here is the outcome variable that I'm reading into my function. Here is my covariate. And again, notice that I'm using the centered version of temperature. I have 2 proposal sigmas to demonstrate for you guys. So at first of all, there's not a ton of damage we can do with a model this simple. But this is as much damage as I can demonstrate on screen for you guys, where my proposal distribution has standard deviation of size 10. Recall the order of magnitude of our parameters. Alpha is like 3, beta is like 0.3, and sigma is like 0.5. I'm going to use proposal standard deviation of size 10. It's adaptive. It does adapt based on the different accepted samples, but that's what I will start. This code here just names the parameters for easy reading. And finally, what is my total number of iterations that I will run? I'm running all my samplers for 5,000 so we can compare across easily. And burn-in. Remember that we're starting off at a random starting point. So here, this chain, I'm starting at 001.097. And if I run this again, notice that my starting point changes. Okay, I want that. I don't want my results to depend on where I started my chain. Because I'm starting my chain at a random spot, I need to discard the first few samples because they did not come from we have not yet found our posterior with our random walk. So arbitrarily, I'm setting my total number of iterations at 5,000 and my burn-in at 1,000. Well, let's run our first chain. I have 2 more chains here, by the way. We have to manually do them, and my starting points change, right? This starting point is different than the starting point for the third chain. I'm hoping that all 3 chains, regardless of where we start them, have found the same posterior. All right, let me run it. It is done. Now it gives me warnings, and that is one indication that there's something off with our proposal sigma, but we did get results. Let's take a look at our acceptance rates. It's 52%. This alone doesn't bring up red flags. If it was something like 95%, then something would be terribly wrong. If it was something like 5%, something would be terribly wrong. 52% is typically just fine. So that alone won't tell us anything. I have to plot my chains. Okay, so let me talk about this. These in no way are stationary. They're still moving around. There's a clear trend here. There's a clear trend here. And what is all this? There's a set of samples that I took that is probably around our starting location. There's also a set of samples I took over here because my proposal standard deviation had to be tuned on the fly until I finally started getting somewhere into the correct range, although not really yet. So it's too large. Let's reduce that a bit. Say 5. And that is the second kind of plot. Acceptance rate actually went down to 25%. Again, that alone does not give me pause, but these chains look ugly. In fact, the worst that the chain will look is here on the bottom, right? Your posterior is bimodal. Depending on where we are inside the chain, we're either concentrating around this value or that value. So where's our estimate? Where's our estimate? Even our intercept is bad. Look, for beta, there's no way that's a stationary chain, right? The variance, the mean, call it roughly constant. The variance in no way is. This next plot just plots all the samples, and there's some weird bimodalities there that I really don't want. I want our chains to converge to the same posterior. So let me go ahead and use the better proposal standard deviation. One good way to think about proposal standard deviation is think of it as being on the scale of the parameter. Our alpha, our intercept was like 3. So that's why I'm using 1 as the proposal standard deviation here. Could I use 2? Sure. Could I use 5? Could probably get away with it. But I went ahead with 1. This has to be tuned. This is the trick of using Metropolis-Hastings. My beta coefficient was like 0.3. So I said, okay, 0.1 is probably a pretty good order of magnitude of my proposal standard deviation. My sigma was like 0.5, so 0.1 is another good one. All right, set this off. It runs. It actually gave me an error, and not every time that I run this, it will give me an error because it starts there. At that time, it did not give me an error because it starts the chain at a random spot. All right, there's my acceptance rate. Again, alone, it tells me nothing, but now I can plot my one chain, and it looks like at a certain point, I am converging to a stationary distribution. I'm converging to a stationary distribution. So for now, I'm still getting this bimodality, but the chains are finding that posterior distribution. So what this tells me is I should probably adjust the number of iterations that I take. And so I will burn it in for 2,000 iterations and end up taking 6,000 iterations. Let's try that. So notice right now I'm working with just one chain because I don't want to waste my time with the other two if I haven't tuned the proposals and a number of burn-in samples. That right there is a start of a good thing. Yeah, you know, if I'm really being picky, I probably need to burn it in a little bit longer. Probably need to burn it in a little bit longer because that sigma looks a little funky. But the other two chains are looking a lot more stationary. And again, this produces two plots, of which the first one is particularly informative. Finally, let's run it for 7,000 iterations. I will discard the first 3,000. All right, now we're looking good. I still want to make sure that all three chains converge. I want to run my convergence diagnostics. So this is just a good first step to kind of tell me that I probably have my proposal standard deviations pretty decently spaced out. They're probably okay. I'm not seeing bimodality weird linear patterns in my posteriors. I'm probably converging to the same posterior, to the true posterior here. So let me go ahead and adjust the sampling parameters for these next two chains. I'm running all three chains for a total of 7,000 iterations, and I'm discarding the first 3,000 based on my trace plots. All righty. And again, my acceptance rates are well inside the reasonable range. We're looking for things like 10%, 90%. You know you did something real off there. 45%, 50%, that's just fine. We're going to use the CODA package, as you guys have seen plenty of times before, to plot our chains, and that looks reasonable. The chains are well mixed. The red, the green, and the black are all covering the same parameter space. There is no trend, visible trend in those chains. We're seeing what resembles chubby caterpillars, not slithering snakes. We can summarize the posterior right there and run my convergence diagnostics. Here is my R hat. Hey, look, they're all ones. Makes me happy, which means between chain variance is the same as the within chain variance. I have very strong evidence of convergence. How efficient was my MCMC? All right, my effective sample sizes are all around 1,000. How many did I plan to take? I took 7,000, but I discarded the first 3. So I took 4,000 samples per chain. 4,000 samples times 3 is 12,000. So although I took and accepted 12,000 samples, only about 1,000 of them were independent. Only about 1,000 of them were independent. So the efficiency is about 1 out of each 12 is an independent piece of information about the posterior. Okay, we'll record that. My effective samples were all around 1,000. I'll even write it down here. And of course, that will vary based on the priors. That will vary based on your proposal standard deviations. That will vary based on how long you run the chains. That will vary based on the burn-in. Remember, that is what constitutes good MCMC. That comes after good science and good statistics. Now we're all about good MCMC. Before, oh, how does that inform science back in the beginning? Okay, that was Metropolis-Hastings, the random walk. Next is a Gibbs sampler that I'm actually going to do via JAGS. You guys saw me hand code a Gibbs sampler, but that's not all that, you're not going to, in a realistic analysis, you're not going to hand code your Gibbs samplers every time. JAGs, as we saw last time, are or a few times ago, a very, very popular tool to estimate Bayesian models because they have programmed all of the little recipes into JAGs. So it won't let you sort of get away with not using the right recipe. JAGS is a standalone program that I provide the links for here. I've only tested the Windows one because I'm using a Windows computer. I don't have a Mac to test. I give you a link here, but again, I'm sorry that I'm not able to test Mac software on my Windows machine. I've also never ever used a Mac in my life. I'm aware it's good. We're not going to argue on camera about it. So step one is for you to download and install the JAGS standalone program. Follow the prompts, follow the instructions about how to install it. Then we need to install the R package that will help us communicate between R and JAGS, and it's called R2JAGS, very intuitive. And if I run this, if I ran this, with a clean RStudio, and I've been working on this, so it's already loaded, it would report that it has successfully linked to JAGS version 4 point something something. So make sure that it reports that. Otherwise, there's a problem with your installation of the standalone JAGS program. I think the theme of Gibbs in general and JAGS, which, by the way, stands for just another Gibbs sampler. The theme of JAGS and Gibbs is that we have to do some mental gymnastics to play the game. We have to use a specific kind of prior to fit the recipe, and we have to play the game with JAGS. For example, your data must be a list. You can't just read in your data frame. It must be a list. And so here I say, okay, here is my data frame, and I'm making a list that has my outcome variable, my covariate, and then annoyingly, for some reason, you have to give it the total number of observations. For some reason, it can't compute that automatically. Then I have to give it a function that computes my model using sort of JAGS language. JAGS language is very, very, very similar to R. In fact, if you know R, you're going to be able to read this. So first things first, the log likelihood will loop over n observations. So it's actually going to sum something n times. So R did that in a vectorized format. We have to use a loop in JAGS to make it happen, right? So we're here actually specifying the likelihood of each observation. So each observation came from a normal distribution with its own mean and its own 1 over the variance, right? So remember, the theme is we need to do mental gymnastics to play the game. So all normal distributions are parameterized in terms of 1 over the variance to make that inverse gamma conjugate prior work. So tau is it's called the precision, which is 1 over the variance, which makes sense. Larger variance, smaller precision, smaller variance, bigger precision. Okay. And finally, to make each mean, we're going to put it together using our typical regression equation. And here is my centered temperature right there. The priors, you guys can read this, but again, all normal distributions are in terms of the mean, 3 and 0. And no, I did not change my prior standard deviations. These are 1 over the variance. And so this is has a variance of 2, and this has a variance of 2 to match what I did up top. Here is my exponential distribution that I'm assigning to my sigma parameter. But remember, I can't use sigma. I need precision. So here I am remaking the precision by taking 1 over sigma squared. Sigma squared won't work, so you have to go sigma times sigma. Very good. So I run this function. Next, it needs a function that generates random starting points for each chain. So I just randomly generate my intercept, single, sample from a normal, generate my slope, and the sigma I generate from this uniform, which gives me a random number between 0 and 1. Make sure that you don't generate a sigma out of a normal, because you can't make it work with the negative sigma. We have to name our parameters. You can tell it to only output a few of your, say, 300 parameters. All right. Finally, let's run the Gibbs. Here is the JAGS data, how it wants. Here is the function that outputs the initial random starting locations. Here are the parameters that we want saved. It's just these 3, which are all the 3 that we have. Here is our JAGS model file. We want 3 chains. I could run it with 33, but that's excessive. I want to get 4,000 samples from each chain. So Gibbs 2 requires a burn-in when we have not yet converged to that posterior distribution. So I'm trying to match what I was trying to do with the Metropolis-Hastings, 1,000. Total of 5,000. I'm going to discard the first 1,000, and I will record every single sample. All right, let's make sure I run everything that I need. And run my model. So it actually will communicate with the standalone program and remind us that we have 315 observations. Remind us that we're trying to estimate 3 parameters, alpha, beta, and sigma. And it is now done. Cool. Print this out. The output of each one of these packages is going to be slightly different, but I think you guys can read it. By the way, as a side note, it automatically reports something called the deviance, which is just the -2 times the log likelihood. That's all it is. It's a measure of goodness of fit for each model. We'll get into that in our next unit. But just to explain what this value, kind of strange value is. All right, there's our alpha, there's our beta, there's our sigma. Here are our R hats. They are all equal to 1. Very good, we have converged. Here are our effective sample sizes. We requested 5,000 minus 1 is 4,000 times 3 chains. We requested 12,000 samples. We got 12,000 independent samples. Very impressive, Gibbs. We got 12,000 independent samples. I'm in love with you, Gibbs. We got 3,600 independent samples. So that is plenty, by the way. So that's about 1 out of every 4.5 that is independent. Okay, much better efficiency than Metropolis-Hastings. You should see this as much better efficiency than Metropolis-Hastings. But for the sigma parameter, it's only about 4 times better efficiency. And we had to play a bunch of different, gymnastics, mental gymnastics to make it work. But it worked. I can make a pretty trace plot. I can find my chubby caterpillars. Yep, that looks like it's stationary chains. They have converged. Happy, happy, happy. If you like the CODA output more, you just put the JAGS output into as MCMC. I'm not going to run this code on screen. You guys can run it. It reproduces what we already know. These chains have converged. Effective sample sizes are 12,000, 12,000, and about 4,000. Much better efficiency than Metropolis-Hastings. The Gibbs recipes are working beautifully here. Remember, Gibbs starts to only become inefficient when we have highly correlated parameters or even correlated parameters, moderately correlated parameters, and we have a lot of those parameters. That in no way describes this particular simple example. I only have 3 parameters. They're not correlated at all. Okay, finally, the coup de grace, our no U-turn Hamiltonian Monte Carlo implemented via BRMS. All right, a disclaimer about this wonderful package. I love this package. I really do. At a certain point, if you ask a question that is complex enough, Gibbs and Metropolis-Hastings will not work. BRMS, you can find a ton of vignettes. The author, Paul Berkner, is great. He's has put so much time in supporting this package. He's incorporated so many wonderful features. We are definitely, when using this package, at the very edge of where statistics is, applied statistics at least. So all of this being said, if we're on the outer edge of where applied statistics is, this is kind of like driving a brand new electric car around, but maybe better than electric car. Electric cars are kind of quite common, like a fusion engine car. You should expect there will be some times when it will fail. So look, it crashes, okay, guys? When you use this package, it crashes. And to my knowledge, it's not clear why it crashes, but just make sure if you're using this package often and you've run, say, 5 models without a crash, go ahead and save because a crash is coming. That's all. Maybe you'll have better luck than me, but with my blue screen of death, not the case. So if you're following along in this lecture, you're down here, go ahead and save everything, save your R, and expect that at some point a crash will happen and we're not going to be upset. We're just not going to be upset because we're at the outer edges of applied statistics. Brand new stuff here. Gibbs is 30 years old at this point. BRMS is 3 years old. So I'm sure they'll work out all these little bugs. This is a really cool package. I'll just shut up about it. It too requires that we install a standalone program. You can't just install the package. You have to install the standalone program called RTools first. Why? The RMS makes actually a standalone C++ program. So it compiles our model in C++ so that the sampling occurs faster. The sampling actually occurs outside of R, and then they bring it back into R. So they actually improved, I think, how to install our tools. It used to be kind of a convoluted process. Ever since R 4.0, it's a much simpler process. I have a link here to read up on it, which includes how it's done in Mac OS that I cannot test. I'm not using a Mac. I don't have access to a Mac. I'm sorry about that. I have tested it on my PC, and following these instructions, which are relatively simple, here's where you download our tools, you install it, then install the BRMS package with all dependencies, and there will be like 15. Again, outer edge, right? 15 dependencies, we're on the outer edge. Then we'll be ready to go. My BRMS is loaded, and you know what? If it crashes while I run, so be it. I will simply reload my R and show it to you anyway. Load my BRMS package. Here, I usually specify a formula object first because I have it. The author of the package gives us this wonderful code that shows us everything that we can assign a prior to inside of our formula. Now, this is important because all the parameters for which we don't assign an explicit prior will get the default prior. And this is the default prior. Now, this happens to be a pretty decent prior for these parameters. But in general, you should be very cautious about going with default priors. We didn't go through a whole unit about how to make prior predictive simulation work and the whole unit about weakly informative priors for you just to take somebody else's best guess at your data. And again, these guesses are actually pretty good. So this is to say, if you forget to assign a prior to something, it will probably still work, but don't make it a habit. Do not make it a habit. It's a way that he makes it so you can start estimating models pretty quickly. So a little bit about this output. Here is the prior, and it's readable. So the default prior is actually a t-distribution with 3 degrees of freedom. This is also a t-distribution with 3 degrees of freedom. That does not match my priors. So I'm going to go ahead and reset the priors. So notice the notation here. Set prior. What is my prior? A normal 3, 2, 3 with a standard deviation of 2. And then class equals intercept. So I set it to my intercept parameter. Next, set prior normal 0 to class equals B. Class equals B means I set the same prior to all beta coefficients. If I didn't want to do that, I can write in here coef equals, and then list the name of every coefficient right as it appears right there for each prior. So you can see if you have 20 coefficients, which a lot of realistic models have 20 covariates, you might not want to set a separate prior for each of the 20 coefficients. So our wonderful author allows us to just set the same prior to all beta parameters. That's what this line does, my code line 176. Finally, here is my exponential 1 prior for the sigma, right? Class equals sigma. We need to make sure that the class here matches the way it appears here. So that's how I got B, intercept, and sigma. All right. Now it's time to run NUTS HMC. This is a no U-turn Hamiltonian Monte Carlo during the warm-up phase. It will optimize the length of those trajectories to make sure that we're not so short that we're basically doing the same thing as our Metropolis-Hastings. We're not so long that we're going to the other side of the world and then coming back because we've hit that other wall. It will optimize them to hit my target acceptance rate of 80%. Recall back to Metropolis-Hastings, it was like 50%. So that alone is more efficient. We have to do less computation. We reject fewer samples. This is how large our trajectories can be. And that is usually just fine. Here is how long I will let Stan optimize those trajectories for 1,000 iterations. It's not quite burn-in, but it's very similar to burn-in. It's, we optimize the trajectories so we don't analyze these samples. This is the total iterations. So the number of samples we get is 5,000 minus 1,000, which is 4,000, which matches what I did above for Gibbs and Metropolis-Hastings. I will record every single sample. I will run 3 chains. I will use 1 core. You can change this, but I know this caused issues for people last time. So I will just go ahead and run the 3 chains sequentially as I've done above. And I will generate my starting locations from a uniform -2, 2. For sigma, I believe it's something like 0 to 6. It just tells us how wide of a random net to allow the starting positions to come from. If you're having trouble with convergence, you can go ahead and, for example, set this to be a smaller random interval. I've used all defaults for all of these parameters. In general, for most models, the defaults are okay. If you're having trouble with convergence, go ahead and change those defaults. Specifically, remember we talked about divergent transitions? Divergent transitions happen when we are not quite approximating our trajectories precisely enough. A way to decrease step size is to increase this target acceptance rate. So you can see, though, it's already at 0.8. It can only be as large as 0.99999. There's not a ton of room to increase this. But if you're getting a few pesky divergent transitions, go ahead and up this to something like 0.9. In general, I haven't had to play around with the length of the trajectory, but never say never. These have to be tuned to your specific problem. You saw me do it for Metropolis-Hastings. 3 chains is plenty. Some people use 4. I have never seen more. I have not seen a ton of applications that require more than 3, to be honest. All right, enough. Let's run it. And I will actually run this, and it might crash on me. So hopefully it doesn't. All right, it says compiling Stan program. So remember, we installed our tools. It is a standalone C++ compiler. My model code, which is the data, the model, the priors, the family, which is Gaussian, which is just a normal likelihood, right? All gets compiled into C++ code, and then sampling occurs elsewhere And then we will bring in the final samples back into R to make pretty plots, to make summaries, to continue. So you can see this is the compilation of the program is what takes the longest amount of time. The sampling itself, because we will have a fairly simple model, will also be very, very quick. But in general, remember that HMC requires that we compute gradients. These gradients are going to be three-dimensional because we have three parameters, right? Alpha, beta, and sigma. If you have 20 parameters, your gradients will be in 20-dimensional space. So you can expect HMC proposals to take a little bit longer because you have to compute those gradients. Because we have a super simple model, you can just take a look at the timings that are being reported. Our warm-up, when those trajectory lengths were optimized, took a third of a 0.04 seconds. The sampling took 0.2 seconds. Each chain ran very, very quickly. It gives us a warning that is tied to the compiler. I haven't figured out how to turn it off. If it's just this warning, you can safely ignore it. In general, warnings don't invalidate the results of the model. I will go ahead and print out the results. Very helpful. It reminds us what our family was, a normal distribution. That's our likelihood. We used no link functions. When we are moving on to generalized linear models, we will use link functions, but not yet. Remind us what our formula was: log, chlorophyll A, centered, temperature, what my data was with how many observations, the fact that I have 3 chains, each one with 5,000 iterations, and it reminds us that we got 12,000 total samples. 12,000 total samples. Okay, estimates look identical. Our hats are all 1. We have converged. Here, I can show off those chubby caterpillars. All right, there are my chubby caterpillars. Very happy about that. We do, however, have 2 different measures of effective sample size. The typical one, the one that approximates the amount of information about the middle of the posterior, is this bulk. This is how many independent pieces you obtained about the middle of the distribution. Call it about your posterior median. This is, so our effective sample size about the posterior median was almost 11,000. That's great efficiency because we asked for 12,000 samples. Our tail is how much information we get about the outer edges of our posterior. Now, here's why that makes sense. The sampler is not supposed to go out into the tails as much. It's designed not to, right? Remember, we go from an anthill, invert it to a bowl, and we roll off the tails by design. And so we will naturally obtain a little bit less information about the tails than about the middle. So we actually have 2 separate measures of effective sample size here. Both of these look great, by the way. This is very, very efficient, 11,000 out of 12,000 requested. This actually means we have a little bit more information than what we requested. This is because of negative autocorrelation amongst successive samples. And here is the value. Here are the values for sigma. All right, let's wrap this up. If you remember, the Metropolis-Hastings had about 1,000 effective sample size for all 3 parameters. We're blowing it out of the water with HMC. Gibbs made us do some mental gymnastics, but did give us perfect efficiency on the first 2 parameters. Recognize that these are basically identical to the Gibbs. Identical. The difference is in this parameter. If you think about it, it's also the one that is maybe most difficult to estimate. If I print out Gibbs again, for my sigma parameter, my effective sample size was 3,600 out of 12,000 iterations requested. Here in HMC world, my effective sample size was nearly perfect, nearly 12,000 out of 12,000. So even in this simple of a scenario, HMC still outperforms the Gibbs in terms of effective sample size. It takes about the same amount of time to run, and I claim, this is opinion time, that it is easier to use this kind of formula syntax than to have to code a model from scratch. Now, we get to understand our model a little bit better maybe this way, but if you're trying to do sort of real science, not to say you couldn't do real science with Gibbs, I have to be careful about what I put out there in the world. Gibbs works great in many, many cases. HMC outperforms Gibbs, even in this simple of a scenario, in terms of effective sample size. And I know for a fact that this R package is very, very, very flexible. And later in this class, I will show you how flexible it is with some pretty cool models. Okay, so this is code is out there. I will repost the data. It should be out there as well, but it's under activities. This completes our unit. We have an in-person synchronous activity on Tuesday. Thank you guys so much for your attention. Have a great weekend. Bye-bye.